Hello, math students. For each function, fill in the table and graph the function. We're going to go through 12 of these examples, and they're all going to be transformations of the parent graph square root of x. Now, without the plus 1 here, just recall that the square root of x was our top half of a sideways parabola opening this way. So we're going to figure out how to do different transformations of this by experimentally plotting points and figuring out what is going on. Y equals square root of x plus 1. Plug in 0 for x. Square root of 0 is 0, and then add 1 makes 1. Now plug in 1 for x. Square root of 1 is 1, and then add 1 is 2. And plug in 4 for x. Square root of 4 is 2, add 1 is 3. Notice that without the plus 1 there, these would all be 1 less. So the net effect of putting the plus 1 there has raised all the y coordinates by 1 point from the parent. So we're going through 0, 1, 1, 2, and 4, 3. And I'm going to put the parent in here. And now we have a graph that is 1 unit higher. Everything's been shifted up 1 unit. It's going to be a good idea to keep track of the parent for each of these. Now when I do square root of x minus 2, plug in 0, we'll get minus 2. Plug in 1, we'll wind up with minus 1. Plug in 4, we'll wind up with 0. These y coordinates are all 2 less than they would be without this minus 2 here. So the net effect is that we have a shift down 2 units. Square root of x plus 2. Notice the plus 2 is inside the radical, unlike up here where it was outside the radical. That's significant. I also didn't fill in numbers over here. I want us to think through what numbers would be used in order to get convenient outputs. For example, if I want to get an output of 0, what x should I use? So I'm going to try to think backwards. What's going to produce these outputs? And the x you need to get an output of 0 is negative 2. Now, if I want to get an output of 1, I want the inside of here to be 1, which means I want x to be minus 1. If I want the output to be 4, then I want the inside, which is called the radicand, by the way, I want the radicand to be 4, which means we want x to be 2. So notice when I plot these points, we have negative 2, 0, negative 1, 1, and 2, 2. The points that used to be on the parent were 0, 0, 1, 1, and 4, 2, but they've all been shifted left 2 units. So putting the plus 2 inside the radical meant that we needed to use x coordinates that were 2 smaller than what we would have used otherwise to get these convenient outputs in order to compensate for that plus 2. So the net effect was that we had to shift left 2 units. Let's see how radical x minus 1 affects things. If I can, try to get these same outputs for y. And what x is required so that I get an output of 0? Well, I need the radicand to be 0 for that to happen, so I need x to be 1. If I want the output to be 1, then I need the radicand to also be 1. So I need an x-coordinate of 2. If I want the output to be 2, I want the radicand to be 4, which means I need x to be 5. Plotting these points, we have 1, 0, 2, 1, and then off our grid here would be 5, 2. But what's happened here is all of the points on the red graph have been shifted to the right by 1 unit. To go from the parent to the new graph, we replaced x with x minus 1, where the minus 1 is inside the radicand. And that had a shift to the right 1 as its effect. All right, this next example, this time there's just a negative in front of the function. So plug in a 0 for x, you're going to get 0 back. Plug in a 1 for x, square root it, you get 1, and then do the minus, you get minus 1. Plug in 4 for x and square root and then do minus, we get negative 2. My new graph also goes through 0, 0, but it goes through 1, negative 1, and 4, negative 2. So what we have here is a reflection of the red graph across the x-axis. In general, if you multiply a function, so multiply radical x by a negative 1, you're going to produce a reflection across the x-axis. What about if the negative is inside? Well, some of you might think, oh, you can't do a square root of negative. Like if I say, what's the square root of minus 4? We get 2i. But as far as graphing is concerned, we don't want that. We're going to be graphing with real numbers only. And so you might think, oh, well, this is not possible to do then. However, x is a variable. If I try to plug in x equals 0, I have no problem with this because negative 0 is 0 and square root of 0 is 0. But if I try to plug in 1, I get square root of negative 1, which is I. And as far as graphing is concerned, we're not going with the imaginary numbers. So you might say, well, then I can't plug in anything for x. However, x itself can be negative. So instead of plugging in 1, plug in negative 1 for x. Then we're going to get square root of negative 1, which is square root of 1, which is 1. If I plug in negative 4 for x, I'm going to wind up with square root of 4, which is 2. And this one also goes through 0, 0, negative 1, 1, and negative 4, 2. In general, if you take the rule of a function and you replace all the x's with negative x's, then you will accomplish a reflection across the y-axis. Next case, what happens if we multiply the square root of x by 2? We'll plug in 0, square root of 0 is 0, then double that, it's still 0. Plug in 1, square root it, double that, we get 2. Plug in 4, square root it, double that, we get back to 4. If you were to do 9, is the next one, square root 9, you get 3, double that, you get 6. So 0, 0 is still a point on the graph, but now we go through 1, 2, and 4, 4. But what's really happening here is that when you take a function and you double it, double the rule, then you double all the outputs of the original. What used to be a height 1 here from x-axis to the red curve is now twice as tall. What used to be a height 2 right here is now a height 4. Whatever height this is, this height here is twice that. So this is not a shifting like a vertical shift because the vertical distances between the two graphs are not the same. There's a 1 gap and there's a 2 gap. This is called a vertical stretching. Notice 0, 0 didn't move though. Any point that's on the x-axis already, like the origin, if you double that height, it doesn't go anywhere. Double 0 stays 0. Similarly, if I multiply the function by a half, square root of 0 is 0 times a half is 0. Square root of 1 is 1 times a half is a half. Square root of 4 is 2 times a half is 1. If I were to go up to 9 and do the square root of that, get 3, and cut that in half, I'd get 3 halves. So 0, 0 is still there. But instead of 1, 1, I'm now going through 1, 1 half. Instead of 4, 2, I'm going through 4, 1. All of the heights have been cut in half. When x is 4, the red graph was 2 units high, but the black graph is half of that. Over here, when x is 1, the red graph was 1 unit above the x-axis, but the black graph is only half of that. This is why I call this a vertical compression. It's also a deformation of the shape. It's not just a shifting because the gaps between these vertically are not consistent. I like to use stretching when we pull away from the x-axis and compression when we squeeze the graph towards the x-axis. All right, next case. What happens if we multiply the input before we do the radical? Now in these ones here, I'm going to aim for this same set of basic simple outputs and ask myself what inputs I need to get there. In order to get a 1 out of this function as an output, I need the radicand to be 1, which means I need x to be a half. The next y-coordinate, if I want a 2 out of this function, then I need this radicand to be 4, so I need x to be 2. Okay, let's put the parent graph in here, and I'm going to highlight some of the points on the parent graph, and let's see where these points are now to get the same heights. So 0, 0 is still on here, so that doesn't go anywhere. But now we have 1 half 1, which is right here, and then 2, 2, which is right there. So we have a graph, looks like a vertical stretching has happened. But what's really going on here is a horizontal compression. Everything's going to get compressed towards the y-axis this time. The red graph was 1 unit away from the y-axis, but after the horizontal compression, that point is now only half that distance. Up here, when y was 2, the red graph was 4 units away from the y-axis. The black graph is half that. So what's really happened here is that everything has been compressed toward the y-axis by a factor of a half. Notice which is the reciprocal of that number 2. Because I had to use half as large of an x to achieve these easy outputs because of the doubling that's going to occur before you do the radical. Okay, let's look at this one here. In order to get an output of 1, I need what's inside here to be 1. So I need the x to be 2. In order to get an output of 2, I need what's in here to be 4. So I need the x to be 8, because half of 8 is 4. So we now are going through 0, 0 still, 2, 1, and then 8, 2, which is off of my scale. We'll just pretend it's over there. But what you're seeing this time, the red graph, when y was 1 unit away from the y-axis. That point, it's twice as far from the y-axis as it used to be. It's been stretched, been pulled away. When y is 2, the red graph, the parent graph, was 4 units away from the y-axis. Now it's 8 units. So what we're seeing here is when the x is being multiplied by a number before you do the radical, like in both these cases, that a horizontal compression or stretching is at play. And it seems to be by a factor of the reciprocal of this number. Right? In the case where that was a 2, the reciprocal of 2 is a half. We're doing a horizontal compression by a half. A red graph is 4 units away, black graph is 2 units away. So the graph has been compressed toward the y-axis by a factor of the reciprocal of that number. In this case here, the red graph has been stretched away from the y-axis by a factor of the reciprocal of this number. The reciprocal of half is 2, so every point is now twice as far from the y-axis as it used to be. So multiplying the x by a number has an effect of a horizontal compression or stretching, and by a factor of the reciprocal of the coefficient of x. Down here, y equals square root of 4x. This is similar. In order to get an output of 1, I need the radicand to be 1, which means I need x to be a quarter. And in order for the output to be 2, I need the radicand to be 4, which means I need x to be 1. We're going through 1 quarter 1 now, so right there, and then 1, 2, which is right there. This is going to give us a horizontal compression by a factor of 1 quarter. So if you look at this horizontally, there's 1 unit gap there along that y equals 1 to the red. Well, to get to the black, it's a quarter of that. So we only went over a quarter. At y equals 2, it was a 4 unit distance between y-axis and the graph. But a quarter of 4 is 1. Now we only go over 1 unit to get to the black graph. So this is a horizontal compression by a factor of a quarter. And a quarter is the reciprocal of that 4. In this case, and this isn't always true for all functions, but in this case, a horizontal compression is equal to a vertical stretching. Right? Doesn't it also look like the graph was stretched vertically to make this graph? Or you could view it as it was compressed horizontally to make the graph. You can look at this one in both ways. And the reason why is because when you do the square root of 4x, you can actually rewrite this function as the square root of 4 times the square root of x. In other words, you could rewrite it as 2 radical x. And when the 2 is outside the radical, it's to be interpreted as a vertical stretching by a factor of 2, which is what we saw up here in this example. The horizontal compression by a factor of 1 quarter is equal to a vertical stretching by a factor of 2, simply because the square root of 4 is just 2. So if you want to pull the 4 out of the radical, it becomes 2 radical x. And something similar is going to happen here as well. In order to get a 1 out of this function, you need the radicand to be 1, so you need x to be 4. In order to get 2 out of this function as an output, you need the radicand to be 4, because the square root of 4 will give us 2, which means you need x to be 16. We can only graph a few of these points, 0, 0, 4, 1, and then 16, 2, I can't graph. It's too far off to the right. Now, it looks like the graph has actually been compressed vertically. What's really happening is that the distances from the y-axis have been quadrupled. Let's look at y equals 1. The red graph was 1 unit away from the y-axis, and after the transformation, we're now 4 units away. But because of the rules of radicals, you can rewrite this as radical 1 quarter times radical x. And radical of a quarter is square root of the top, square root of the bottom is a half. So it turns out that in this case, a horizontal stretching by a factor of 4 is the same consequence as doing a vertical compression by a factor of 1/2. It's not always the case that a vertical stretching can be thought of as a horizontal compression, but in some cases that is true. Okay, we're going to summarize all the different ways that we have seen here to transform a function. If you want to shift a graph up k units, then what you need to do to adjust the rules, you need to add k to the rule. In function notation, it looks like this. So f of x represents the rule, and then you add k after the fact. So as an example, let's apply this to x squared. If I want to move x squared up k, it would look like x squared plus k. And we're assuming k is some positive number, by the way. If you want to shift a graph down k units, then you subtract k from the rule. So it'd be the rule of the function and then minus k. So in the case of x squared, it'd be x squared minus some positive number. If you want to shift the graph right k units, then we need to do a function evaluation at x minus k. In other words, replace all the x's in the rule, all of them, with x minus k. In function notation, it looks like this. You do f of parentheses x minus k end parentheses. So the function rule here is x squared. I'm going to replace the x with x minus k. Use parentheses when you do this. I've created a vacant spot where the x used to be, and I'm going to plug in x minus k there instead. If you want to shift a graph left, then you do the same thing, but you replace all the x's in the rule with x plus k's. Function notation looks like this. You do f of x plus k. Applying it to the rule of x squared, it would look like x plus k, all in parentheses, and then the square. So the vertical shifting is the k is outside the rule of the function, and horizontal shifting, you have an x minus k or an x plus k where the x used to be in the parent graph. If you want to stretch compress vertically by a factor of k, now if this k here is more than 1, then we'll get the stretching. If k is less than 1, we'll get the compression. We just multiply the rule by k. So it looks like this in function notation. You do k times the rule. So if I want to stretch or compress x squared by a factor of k, then I just do kx squared. Now if you want to stretch compress horizontally by a factor of, notice I'm doing the reciprocal of k this time, you replace all the x's in the rule with kx. Right, that's exactly what was happening in a case like this one here. This was the parent rule. If I replace x with 2x, this led to a horizontal compression by a factor of a half. So replace all the x's with kx will be a compression by 1/8 or stretching by 1/8, depending on what k is. If k is general here, k might be a fraction to begin with. So if this k right here is a half, then 1 over a half, this will be a 2, and this will become a stretch. But if this k is more than 1, like 3, then 1 over k will be a third, and that's going to correspond to a compression. And what this looks like in this case is, here's x squared, you replace x, get rid of it, put parentheses, replace it with kx. So if the k is in with the x before you do the square, that's unlike this one up here, then we are talking about a horizontal compression and or stretching depending on what k is. If you want to reflect a graph across the x-axis, you just multiply the rule by -1. So you do the opposite of the rule. So in this case here, you would do the opposite of x squared. Remember what I said about order of operations here. You would square the x and then do the minus. And if you want to reflect a graph across the y-axis, you replace all the x's in the rule with -x. So if we used to have x squared, replace that with -x. Of course, in this case, the negative will be canceled by the square and it'll go back to x squared. That's just simply because x squared, if you take that graph, which is already symmetric across the y-axis, and then you reflect it across the y-axis, it won't be any different. In other words, every even function, this tweak doesn't change it if it's already symmetric across the y-axis. And so there's our summary of all the different transformations you will be responsible for knowing. Now let's put some of them to practice. Here we have some functions on the same grid, plot the indicated transformation. Okay, so this function that's provided is the f of x, right? And our goal is to plot what f of x plus 2 would look like. So this corresponds to the vertical shift. So the key points, I'm going to move everything up 2 units from where it used to be. So there's our new graph. This next one, if I do f of x minus 3, notice the minus 3 is in with the x. This is where you replace x with x minus 3. That's going to be a shift. Let's refer to our table. If you replace all the x's with x minus 3's, then we are going to the right 3 units. So this entire graph needs to go right 3 units. I'm going to start with that point there, move it right 3. It's actually going to fill in perfectly where that gap is. Move this point right 3, it's going to be there. And then the v, I'm going to make this a different color. Okay, so the black graph was moved to the right 3 and it makes the red graph. In fact, why don't we do all of the new graphs red, which is different than we did up here, right? Up here, the parent was red and the new graph is black. So don't let that throw you off. Here, the black graph is the parent and the red graph is the new one. Put a negative sign in front of the function, negate the rule of the function. This will be reflect across the x-axis. So every single point, let's focus on that one first, is now this exact same distance but on the opposite side of the x-axis. Right, so we're going to get this portion there. Our v is going to go up this time, crossing the x-axis at the same location as the other one crossed the x-axis. So there's our reflection across the x-axis. When you do f of negative x, this is where we reflect across the y-axis. Focus on that point, reflect it to the other side of the y-axis. So we'll get that portion and our v will be here and end there. So you can reflect the black graph across the y-axis and we get the red graph. If you double a function, this is the case of the vertical stretch. So every point will be twice as far from the x-axis as they used to be. This point here will now be right there. So we're still going to get a horizontal segment there. Any x-intercept is going to stay the same. This point here will be twice as far from the x-axis as it is now, so it's going to be down to -2. And then let's go ahead and complete this. So here's the result of doing a vertical stretch by a factor of 2. Every point is now twice as far from the x-axis. X-intercepts do not move when you do vertical stretching or compression, right? Because when you double 0, you stay 0. Here's a vertical compression by a factor of a half. So every point in my new graph will be half as far from the x-axis as it used to be. So we're going to get a horizontal portion right there. The intercepts will not change. This bottom of the v will be half as far away. The hollow point will be half as far away. F of 2x. Right, because the 2x is in the parentheses, we are talking about a horizontal, either compression or stretching by a reciprocal of that number there. So instead of 2, it's by a half. So that means we're going to actually do a compression. So this is a horizontal compression by 1/2. Okay, so every point is going to be half as far from the y-axis as it used to be. So the hollow point will be here. The bottom of the V will be there. Any point on the y-axis is not going anywhere because it's already on the y-axis, so cutting its distance to the y-axis in half doesn't do anything. But the terminal point, that point right there, will no longer be there. It'll be half as far. Our graph's going to end right there. So we're going to have a horizontal part right there, and we'll have a skinnier V that ends right there. And here is our horizontal compression by a factor of a half. This is an obvious case where a horizontal compression is not the same thing as a vertical stretching. And then this last one here, we have another horizontal compression slash stretch. The K is a half right there, so do the reciprocal of K, that gives you 2. That tells me this should be a stretch. The reciprocal of K is more than 1, so we're stretching. This is a horizontal stretch by a factor of 2. So we're going to be doubling all of our horizontal distances from the y-axis. Let's start with this hollow point right there. It's going to be twice as far from the y-axis. Let's go down to this corner right there. It's going to be twice as far from the y-axis, so double this length to there. The intercepts move. I should have pointed that out in the last one, but this intercept looks like it's at 1.5. Well, that intercept is now going to be at 3. This intercept looks like it's at 1/2. We'll double that. The point on the y-axis will not go anywhere. But this point here will be twice as far from the y-axis, so it's going to be all the way out to here. And so our end result is it's going to be... Notice when you compare stretching it vertically versus horizontally that, look at this, the height of that sharp corner, it was pulled down. Right? In the case of the compression, it was, this corner here got closer to the x-axis, over here it got further from the x-axis. But when you do horizontal stretching compressions, the heights do not change, right? It was still at -1 height. Same thing here, the peak is at the same height. They're both at -1, the y-coordinate, but it's the horizontal position of the peak that's been moved. We're going to begin with the parent graph of x squared, and the purpose of this slide is to show you that the order in which you do multiple transformations can have effect on the final result. For example, let's do the shift up 2 first, and then reflect across the x-axis. Well, the x-axis is down here, and I'm reflecting this one. So reflect after you've done the shift up. Maybe I'll color code these. Put a 1 there, that was step 1. And then after doing step 2, our final graph was down here. If I start with x squared and I do the reverse order, same transformations but just in reverse order, if we first reflect across the x-axis, so step 1 would put our parabola down here like this, and then take that orange one and shift it up 2. After doing the second step, compare the two reds. They're not in the same place at all. So the order in which we did these transformations was significant. Now in the first case, let's go ahead and show you what the rules would be for each color along the way. So if I started with x squared and I shifted up 2 first, then this orange one is x squared and then plus 2. That is the rule for the orange. I'm going to get rid of these steps numbers. But if you want to reflect now the orange across the x-axis, then you need to negate the rule and make sure you negate the entire rule. So this one should be the negative of x squared plus 2. That's how you take x squared plus 2 as a rule and reflect it. You negate the entire thing. Don't make the mistake of just throwing a negative lazily in the front and write this. This is not the same thing as reflecting this across the x-axis. Over here, we started with x squared and we first reflected it. Negative x squared is what we did there. Then we took negative x squared and shifted it up 2. So the final graph here looked like this, negative x squared and then plus 2. So the two red graphs, here are their rules, and they are different, right? Negative x squared and then plus 2 is not the same thing as negative of x squared plus 2. In fact, what you can do with this first one here is distribute that negative and write it as negative x squared minus 2. And now you can see without parentheses why the red graph in the right picture doesn't have the same rule as the red graph in the left picture. That's why their graphs aren't the same. But notice what's currently circled. I could have achieved this graph right here by doing the opposite of x squared first, which is what this orange one over here is, and then doing minus 2 after. So in other words, take this orange graph over here and shift it down 2, and it will become this red graph. Okay, now we're going to do some multiple transformations. Graph the following function by beginning with the appropriate parent function and graphing one transformation at a time, all on the same grid. Okay, let's start with the parent function, which is, hopefully you can recognize that there's an absolute value involved here, so I'm guessing that we're probably starting with the absolute value of x. So here's our parent function, and we're going to do one transformation at a time until we wind up with this statement. Now my recommendations, if you recognize anything as a left-right shift or a vertical shift, do all the shifting last and first focus on any sort of reflections and or stretching compressions that might have happened. So in other words, I'm going to do the stretching first. What happens when you double a function? That corresponds to a vertical stretch by a factor of 2. So whatever y coordinate you used to have, double it. Right? So double 2 to 4. So all the heights are now double what they used to be. 0, of course, doesn't double, or it doubles but stays 0. So we from 1 to 2 there, from 2 to 4 here, from 3 to 6 here, so that goes just off the graph. And we have an orange graph that's also a V, but a little more narrow of a V. Vertical stretch by a factor of 2. When I say factor of 2, it means by doubling. Factor means multiply by 2. If you just say by 2, if I say vertical shift by 2, then that just means everything went up 2 units. When I say vertical stretch by 2, that means we multiplied by 2. I should probably write the word factor of 2. Okay, next, let's worry about doing that negative, get that in place. And when you multiply a rule, and the rule we're multiplying is the orange one, we're going to multiply the orange by negative. And when you do that, you reflect about the x-axis. So take the orange and reflect it across the x-axis, and it's going to make... Now that we've gotten the reflections and or stretchings out of the way, now let's finish with the horizontal and vertical shifting. Let's do the horizontal first. To go from green to blue, I erase the x and replace it with x plus 1. In other words, the plus 1's inside the absolute value. And when you replace x with x plus 1, then we have a shift left and then 1 unit in this case. So now we need to do a v that has been shifted left 1 unit. Or you could have done something like this, just kind of grab the green and shift it left 1 unit. Right, so the blue is where we're at now, and then we have only one more step to do. We got to do that plus 4. That's going to be our shift up 4 units. So to go from blue to purple, the only change I made was adding that 4, and that's going to shift up 4 units. Okay, so I could just grab the blue, and here's the blue, go up 4 units. The sharp corners right there. Now I want to make that purple. And there's our final graph. Now, these do go down forever. The domain and range, I don't ask for it, but I could now. The purple graph goes left and right forever, so the domain is all real numbers, but the range is limited. Right, the highest point on the purple graph is at height 4, and every height below that is achieved. So the range is negative infinity up to 4. Graph the following function. This one has a bit of trickiness to it because there's a coefficient of x and a plus 8 next to it, all inside the square root. Well, do you recognize that it's definitely the square root of x is our starting point? I'm going to multiply by 4 next. This is just a horizontal compression by a factor of 1/4. So we've actually already done this one. But then how do we go to the next phase? Here's the danger of what a student might say, that now I'm going to put that plus 8 there and say, okay, well that's a shift to the left 8 units. But the danger here is, in order to accomplish a shift left, let's read this carefully. To shift left k units, you replace all the x's in the rule with x plus k and use parentheses. When I just lazily throw a plus 8 after the x, then I haven't actually replaced x with x plus 8. If I were to replace x with x plus 8 to make the shift happen, then you would have to use parentheses and it would look like this. This corresponds to a shift left 8. But when you remove the parentheses, this would be a 32 here instead. So here's my advice. When you have an x plus or minus a number right away and there's a coefficient of x, be careful. This is a dangerous spot. I recommend you factor that 4 out and look at this as if it had parentheses. Now I can see what the actual shift is. It's a shift left 2. To go from the orange to the green, we want to replace x with x plus 2. And when I do that, there's an x plus 2 there now. So now we have a shift left 2 units. And then, of course, if you distribute the 4, it looks exactly like what we are aiming for. So take the orange and shift everything left 2 units. And I didn't ask for domain and range, but let's go ahead and do it. As far as x is concerned, the graph only starts at -2 and goes to the right. So we have a domain of -2 up to infinity. And then the range, we start at a height 0 and go only up from there. So the range is 0 to infinity.